Let's get this into the form that we always like. What am I going to call this?
You're going to call it K.
If it was a function of time, I would call this omega.
Yeah.
But this is a function of x, so I'm going to call it k. So k.
You want K squared.
What's that?
You want K
Oh,
squared.
k squared, thank you.
You want it
Yes.
to square
So
it.
k equals 2men over h bar squared. And this is called the wave number. And remember, it equals 2 pi over lambda. I like to think of it like omega is an angular time velocity. This is an angular spatial velocity, but it's called the wave number. All right? And so now we have, this is sine n prime of x plus k squared sine n of x. And recall there are 3 solutions. Remember our standard 3 solutions?
Underdamped, critically damped.
That's interesting. Okay, so here are the general solutions that I know. General solutions that I know. The 3 general solutions. It's psi of x equals c1 e to the ikx plus c2 e to the minus ikx.
Oh, those ones, yeah. And then,
Right? Or we could have psi of x equals c1 sine kx plus c2 cosine kx. Or we could have psi of x equals like c1 sine kx plus some phase. They're all solutions to second order differential equation. You need 2 boundary conditions to solve for the 2 arbitrary constants.
so certain situations will work for one of those 3 solutions.
Exactly. That's why you want to have these at your hand.
Yeah.
When we solved for the infinite square well, what solution was the best choice?
The sine x, cosine.
Okay, why?
Because
Well, has a wave function.
It has to do with the boundary conditions. The boundary conditions, the wave functions went to 0 right here and
ends,
there,
yeah.
right?
I would say because that equals C1.
It was because
Okay, yeah, because we can solve it easily.
it was for the first one that in order for it to be 0 on both ends, you got 0 solutions for everything, so you got nothing. You couldn't get any real solution.
Okay, yeah.
Basically.
Okay, so what we're going to look at here, the next question is what are good boundary conditions for a free particle? All right.
Negative and
Yeah, I mean, certainly does the wave function go to 0? Do you think it? So what happened is when we had an infinite well, we had an infinite potential, and we knew we plugged the particle in there. And if the potential were truly infinite, we know that we couldn't get the particle outside there. So the wave function was 0 over there, and the wave function was 0, but it lived in here.
Yeah.
All right, are there those restrictions on the infinite square well?
No, so you use
No.
the first one.
All right, so you got to use the first one, right?
We could say it goes to 0 at
Yeah, the first one.
you could say it goes to 0 at 4 billion light years.
Well, you can't really say that, right? I can't say that unless you know something I don't know, Jeremy. All
At
right.
the edge of the universe.
Yeah.
That's
All right. So I don't
But
know.
is that the boundary? The universe.
And so what I'm left with is using this solution.
Sounds like infinity to me.
All right. And so let's look at this. So what we're going to say then. So here are our basis sets right here. So I should say Kn and stuff like that, but I'm going to lose the subscripts anyway because I'm going to be continuous later. Kn. Okay, so these are our basis sets. These are our solutions to time independent problem. All right, let's just take a look at our full solutions and see if we can recognize what these things are. So let's look at psi n of x and t. And what do those things look like now? So how do I build that from here? So what I should be hearing is, oh, well, all you do is...
Psi x times e to the negative
There you
I.
go. All you do is multiply it times the time-dependent part. All right, so let's use the time-dependent part and throw it in over here. All right, and let me see what I can do here. Okay, so here we go. Okay, what I'm going to do is for En, so let's write it out. E to the minus I, En over h bar t times c1 e to the I, k, n, x plus c2 e to the minus I, k, n, x. Okay, so what I'm going to argue is that these things are going to end up looking like plane traveling waves. All right, I'm going to end up arguing that these things look like, I'm going to argue that this first one looks like a plane traveling wave this way, and that this one looks like a plane traveling wave that way. All right, now, if these are plane traveling waves and they're traveling waves, what's another expression for En of a true wave? It's h times the frequency.
Yeah.
All right, but in terms of omegas and h bars,
H bar times omega.
h bar omega. All right, look at h times frequency equals h over 2 pi times 2 pi over a period, which equals h bar omega. Right? So, when I bring these through, this becomes, my total wave function becomes C1e to the I, okay, knx minus omega t, all right, plus C2 e to the I, e to the minus I. Let me see what's the best way to write this. Knx. Yeah, I guess plus omega t, right? All right, let's do some mental gymnastics. What we're going to do is we're going to pull out a k from these things. So this is C1e to the I kn x minus omega over kt plus C2. I might have to fool around with this in a minute, right? I want to do it this way, I, K, N, and so how would I do it? Minus X. So minus X minus omega over KT. Did I get that right? Did I get that right?
Yeah, just distribute the minus sign.
Yeah, because they're both minus, yeah. All right, and what do I recognize omega over K as?
Velocity.
That equals velocity. It's 2 pi over the period, all divided by 2 pi over the wavelength, which equals wavelength over the period. And wavelength over the period is a velocity. Is that potential? Is V potential there?
No, it's
Okay, it's velocity.
It's not
That's
voltage.
the velocity.
It's not voltage either.
And it's not voltage. What's that, Elmar?
That's the velocity of the traveling wave.
That's the velocity of the traveling wave.
You're leaving out the G of T aspect. Oh no, you have the wrong line, I'm sorry.
That's it. This is the
Yeah,
GT
yeah,
right there.
yeah.
Yeah. So to form the full wave function, I've got this thing. Okay, so what this all equals, this equals C1 e to the I k n x minus vt plus C2 e to the I k n, I guess it's minus x.
Minus VT.
Oh, no, then I want to leave it this way, guys. Sorry. Let's pull this out, make this minus. This is x plus vt. Yeah, sure, that's the way I want to do it. This is the correct form. Okay, sine n of x comma t. Okay, now, what do you recognize a function of x minus vt as?
Position minus another position.
Okay, so, I might lose this picture over here.
Well, if you had a function of x, then the dt just changes that position with respect to time.
Yeah, so let me try to see if I can draw. I don't know. I sometimes see this and I sometimes lose it. All right. Let's add, and I think I've got this for purpose anyway. Here's some function of x, and t equals 0. Right. Let's say that this is a plane wave and it travels at a velocity v. Right. So in a time t, how far does that go? It goes some distance x. So x equals vt. All right, so at some later time, this thing's going to come out and look like this. It's going to do the same thing. But this is going to be f of x of t. All right, now, f of x of t equals 0 equals f of x minus vt. So what I'm going to do is I'm going to say, here's f of x at t equals 0, right? I guess I have to call this f of x 0. And then here's the shape of this wave function at some other position x. But if I take this position x and I subtract from it vt, then that puts this thing right back on top of here.
Can they do something like this with the, when you normalize to show the time independence of the normalization? Is there something going on there or no way out?
I'm not sure about this.
No,
Yeah.
it wasn't. I think that was in Griffiths because he just showed that you normalize it, you get that same wave function, but then the time depart just shows that it's just propagating through space over time.
Oh, maybe. Yeah, maybe you guys read something that I didn't quite see. Yeah. But this
you
is
were
a
saying
time
you
line.
said position. Do you mean time instead? I think before you said something about
Okay,
the
so-
position changes. But
Yeah, so what this is, so I'm missing words here. But I guess it's this, is that this function of x and t, if this function of x and t equals f of x minus bt. So I think this is the conclusion that we're trying to get. That if you have a general function, a function of x and t, and it's equal to x minus bt,
yeah,
then all that does is it represents a shape that's traveling at v, so that shape is then superimposed at some time later, and some distance later, by a distance equals velocity times time.
Is it x minus vt is really distance, so is there a comma t equals 0 when you have your f of x minus vt, comma 0?
So maybe do this, right?
T equals 0?
And that would be right, yeah. So if you have a function that looks that way, what that function is telling you is that it's a shape. And that shape is traveling at a velocity v, right?
yeah.
And in a time t, that shape at a velocity v travels a distance x equals vt. So if you take that distance that it's at, x, and subtract vt, that brings you back to what that function was at time 0. So it becomes the initial shape that it was at time 0.
So you could
I
change
think
that.
I
left.
actually did a decent job at saying that,
Yeah.
even though it's confusing.
But the top thing, that left f of x and t, shouldn't that just be f of x? Because the t is equals 0. You're just saying that it's f of x for all time. Right?
Yeah, for all time. I think this is
Yeah.
fine.
Yeah,
F for all x and for all time.
yeah.
It's literally equal to a function of x minus vt. And so you don't need a 0 for time, right? It's just not even there. And that's what we have over here. We have a function of x minus vt. Alright, so Matt, I think you were following me there in words for a little bit, right?
Yeah, it looked really good on film, so we got going on with it.
Okay, it's going to look worse on video. Okay.
I'll
All
edit
right,
that
at least
part.
I'm alive these days, all right? Those are the worst videos I've ever seen in my life. I'm so embarrassed. All right? So what can we reckon? And this is very nice to know. If you get a function, no matter what it looks like, if it's a function of x minus vt, it's a plane traveling wave going that way at velocity v. Now, what do you think if you get a function of x plus vt it is?
Plane traveling wave with opposite velocity.
Going that way. So the conclusion is that the solutions for Schrodinger's time-dependent equation for a free particle is a linear combination of a free traveling wave going this way and a free traveling wave going that way.
Right, but because it could be in all space, it doesn't have to be just x. That could be y, z, and y and z, right, as well.
Yeah, we're only doing one dimensional problem, but yeah, okay.
Yeah, and thinking on that second piece of it, it would be like x of x plus vt, comma t. The second one then.
So this would be
X plus vt.
plus vt, yeah, good.
Comma
X
t.
plus
To
vt.
describe what you're saying. Yeah.
Yeah, I guess. Because this is putting us at a distance vt
Right,
away.
later. Right.
Yeah. So let's do this. F of x 0 at t equals 0. This is f of x 0 plus bt. All right, not the world's greatest explanation there. I'm sorry about that.
Griffiths does a good job, though.